Hello, everyone. Thank you, Jakub. I think I am between you and the weekend, so I will try to be on topic all the time. So this is a presentation about IOTA Smart Contracts. It's not new topic, and actually it's time to update the first of all the IOTA Foundation internally about what's going on, what we do, what we think, and where we're heading to. So mostly, like Jakub already said, it's technical, but it's also a general more presentation because I feel it's necessary since it's since October, so it's about 3 months. It was 3 months. So we kind of, from one side, it was a so-called pre-alpha release, and from one side, it's fundamentally, we didn't change much, but from the other side, talking about the some perspective and some important parts, which especially are well seen from the development side, from the developers side, to the smart contract, they change significantly. And while for some of you, or for many of you, were discussing all these concepts around for quite a time, but still, I think it's necessary to put everything into perspective and to, like I say, it's to introduce the animal, what we're dealing with. It is. It's not easy to tame, and it's very powerful stuff. So actually, that is why I think it's also this presentation is needed to spread the ideas around, to understand the scope of it. I mean, and to have a good feeling when working, for example, on the very important project of the IOTA Foundation, which was announced recently. Some time ago. So that is the goals of this presentation. Actually we're talking about the features who are implemented as the code in the WASP node, and hopefully it will go alpha in coming month, and we want to go out something very practical things, not maybe finished yet, but still already practical things in coming weeks. I hope in January. So what I will be talking mostly, it's not what I was talking previously early on these topics, because the main focus before it was on the consensus about the committees, about the non-forkable chains, about the WASP nodes, and overall structure of the distributed system. But then when we are done with this distributed system, we have clear concept how it works, and we implemented it, at least in the first initial versions of it. So we go deeper into the semantics of the IOTA smart contracts as a tool to build applications. This is important, actually, important thing to stress, that we are creating a tool for others, and it's actually it's always we're creating a tool. The ledger, the distributed ledger of the Tangle and everything is a tool, but this one is also a development tool, an environment where you write the programs which are called the smart contracts with very special characteristics in the market. We all know them. So actually, I put some idea of that the multidimensional structure of the IOTA smart contracts, meaning that actually when we're talking about these multiple chains approach and so on, suddenly you realize that you're putting a lot of power into it, a lot of power which are not present in other DLTs and smart contract platforms. However, at the same time, we are putting a lot of complexity in it too, which we have to deal with it as a developers of those tools, and probably, possibly, or whatever, it contains also attack vectors or some unexpected surprises. So these are dimensions. We are adding dimensions to distributed ledger, let's say. So I would first of all we'll talk a little bit about the perspective. So when we have a classical smart contracts, classical means Ethereum. It's for me classical smart contracts are Ethereum. I think most of us agree with that. So what are these? Actually, we have a very cute, very nice, very perfect system about running trustless computations, which are called smart contracts. And I keep saying always that actually we cannot invent too much new here, because they are perfect in a sense that they are smart contracts, the immutable programs running on the Tangle. They are the essential features of it, and it's fundamentally linked to the concept of the smart contracts, how it's most people understand, developers and the market as such in general. That is one state machine which they interact via synchronous calls on the same state. So when you go deeper into the thinking of people about smart contracts and talking and what is meant by smart contract, you have some very comfortable environment when you have a state, global state, which is stored on the blockchain, and all these smart contracts are calling each other and sharing on the same state, even if they cannot access the variables there. But it's like in the program which doesn't have multi-threaded environment or something, it's all synchronous, right? And this is what is conveniently understood as the global state, and everything which is comfortable, which comes from that fact, and the power of it. The power, I mean, the solidity, the everything. So but it is very really nice thing. However, all we know that it has very fundamental flaw. It's not scalable by the design, and certainly, of course, it's far from what would be the Ethereum. The power of Ethereum is huge, and the capitalization is huge, but it's far from what is needed by could be the demand for the smart contract like services facility from the market. It's far from that, so we need scaling and so on. So normally what you do when you realize that you have one chain, and this is a cause of all reasons, you want to have second chain and more chains to run them in parallel. So the fundamental fact that the on blockchain classical smart contracts don't run in parallel. And you want to run them in parallel, so you run another chain. Then you immediately understand that when you were within a blockchain, you are in the comfortable environment of your smart contract programming, all these ERC20 or the Chainlink oracles or whatever they're calling, or Uniswap or markets or whatever smart contracts actually is just a procedures or subroutines or with one big state machine of one big program. And when you're going to another blockchain, suddenly you realize that another blockchain is another blockchain, another consensus, and another comfortable environment. In between, there is nothing. It's empty intergalactic space without laws of nature from the point of view of the smart contracts, from that comfortable environment. And then this is then we of course implement, there are ways doing that, atomic swaps, or relays, trustless relay chains, or similar stuff, and so on. So this is how it is, what are smart contracts classical and how they are evolving. Let's say we trying to solve fundamental, actually root of all problems, including the price, including the cost, everything. Fundamental problems coming from the poor scalability. So now what we do with IOTA smart contracts? Actually, again, it's nothing new, but it's also new a little bit compared to how we were talking about it 3 months ago. We see at IOTA smart contracts as multiple chains, multiple blockchains. We call it chains because it's shorter, but it's a blockchains, right? Multiple blockchains are all anchored on the Tangle. And each blockchain has comfortable environment for its multiple smart contracts deployed on it. So actually all those smart, which I'm showing here, I hope you see my mouse pointer. Yes. This is a blockchain and they're comfortably deployed all the smart contracts. So these are dynamically linked programs which you put into the blockchain, then they become immutable and they become part of the program, the whole stuff. Each of them is a smart contract, just like in Ethereum. They call each other synchronously, which means, what does it mean? It means that they are working on the same state. In practical terms, it's if one smart contract is calling another and passing some tokens, yeah. So when the call returns back, the called smart contract, the target smart contract has those tokens in its account, and the next call to it has to take into account that it already had that balance of tokens. So these are synchronous calls. And they are all working synchronously on the chain state, on the blockchain state. And this is a one chain in IOTA smart contracts. So if we are looking at from this perspective, I keep saying that it's functionally or semantically equivalent to Ethereum, which is a perfect platform, let's say, with all non-scalability problems, of course, because it's a sequentially added, sequentially updated blockchain. It cannot be like this. This very fact of the being sequentially updated gives you comfort of the global state. However, it gives also negative sides. So the non-scalability. Now, and why we can do this? We are very good with the Tangle. The Tangle is not a blockchain. The Tangle allows you to run parallel states. Okay, Tangle is also eventually global consensus, but still, especially with the UTXO ledger, with the new implementations on the Gossamer, which are coordicate line of development, and also Chrysalis, of course, we have possibility to run on the ledger parallel states, which is impossible on blockchain. So that's why we can do many chains, many parallel chains. And again, we have some problem of the intergalactic space without loss, but here we do not have this problem, or rather we can solve it easily because we have a value tangle, the so-called layer 1, which is global, which is parallelizable. And what we can do is to transact between smart contracts on different parallel states, parallel chains, trustlessly. Meaning that we are not leaving the space of laws of nature, and the inter-chain space is filled with laws which are defined by the value tangle. So that's why we are able to send tokens from smart contract, in this case 7003 from chain, which this ID, send tokens to smart contract 3037 on another chain without having to care about, do we trust the medium of sending or not? We don't need to trust because it's a tangle. It's a ledger which is has its trustless characteristics of trustless and distributed consensus. So this is the basic picture, and what I want to say, each chain can be on IOTA smart contracts. Each chain can be small one with even one smart contract. We demonstrated that in October. Each chain was one contract. Yes, it's a very lightweight structure. Of course, each of them are run by the committees, but we skip for this part now. But anyway, it's separate consensus for each chain. So it can be very lightweight. It can be 1, 2, 3, 5 contracts, but it can be heavy. I believe maybe Ethereum contains tens of thousands, maybe smart contracts, different of them, all of them synchronously tied, each with other, which is a very heavy constraint. So we can have it small, we can have it big. And it's up to you, up to us, up to the use case, and it's invites you to use this feature to, for example, parallelize your distributed application, the app, in a way that you want it to run on several chains. And it gives extremely huge power to the development of these applications, because you have still the possibility to transact in the trustless way, in easy and embedded way. Okay, maybe I will talk later, but maybe not about how to do this, but still there is a possibility, at least a theoretical. Same way, this is a big power. Same way, it adds this feature. We have the ecosystem around Ethereum. So this ecosystem is around one blockchain. So, and they are still having a lot of discussion considerations about what and how and so on. And here we have another dimension. The new dimension always adds the order of complexity. So this is a one-off messages, because with power, it's coming many other aspects, which sometimes it's very important for us who create this very tool. I'm not talking about that each of them is run by the committee. So it's we have a permissioned aspect, which is immediately involves that someone has to own the chain, someone has to decide on the fees who are on this chain, and so on and so on. We have entities which do not even exist on the classical smart contracts. So, but the power is of it, of course, it's also on the order of magnitude higher. So when we introduce this multi-chain approach, where yes, when the assets can travel in between chains and between layer 2 and layer 1 in trustless way, we immediately open the box of many other decisions, what we have to do. So I would just want to go through it. So it's a multi-ledger stuff. So we have a value tangle, which is level 1 ledger. So we have addresses, UTXOs, we have transactions, everything. We will have soon codes and all kinds of stuff. And we have colors, by the way. We have color tokens, which is another dimension, extremely powerful. And each chain is our parallel ledger. So we have many ledgers. It's a multi-ledger system, the IOTA smart contracts. So now we have actually two types of securely identified agents. Let's call them agents. It's usually in DLT you have one, or at least in Tango have one. This address. It's someone which is represented by the address. So behind you have a private key, and you as an owner of this private key, you are securely identified in the system, and you are able to move tokens. You are able to do something this and that, and you are securely identified. If you would receive a transaction or tokens, you know that it's signed, this transaction, and you know that the signer owns the private key. So here we have one more securely identified agent. It's on the level 2 agent. It's a smart contract. Smart contract has to be securely identified. There is no other way of doing that, because he has to have control of its funds, of its data, and he has to be securely identified when transacting between chains. And of course, it immediately means that you have on the layer 2 here, for each smart contract, you will need to have separate space partition, just like, I mean, local state, local variables and whatever. Now, again, going deeper into this thing. So it's easy to say that smart contract is holding, controlling its funds. Yeah, you of course let's forget now for ERC-20. ERC-20 are not really tokens in the sense of the distributed, or in the sense of the underlying ledger. They are level 1 up. So let's not talk about it. We're talking about the assets who live on the underlying ledger. So if you say that someone is controlling, smart contract is controlling its tokens, color tokens, by the way, you have IOTAs, you have green, you have red, and whatever code you have, tokens, it means that only smart contract has to be able to move them. It means that there is an account which is controlled by the smart contract. And then it of course, it extends what I was saying before, that you have chain, you have smart contracts, and each smart contract actually has an account. For example, this one, 3037, has state partition on the chain, but it also has the account which is controls here. And in this account, it has 5 IOTAs, right? From the other side, when you're talking address, so address is normally you have some IOTAs in your address. When you ask for Goshimer Facet, he will, for some reason, allocate you, give you 1,337 IOTAs. And you will have these IOTAs in your address. It's in a wallet in your address, and you can move them. However, if we want the address to be an agent who is able to control tokens, we immediately have the concept of the accounts controlled by those address on chain, in the on-chain ledger, which means that you actually have address which is on IOTA Tango. The value Tango controls this amount of IOTAs and 42 red IOTAs. Also, the same address controls 42 IOTAs on the pink chain. And it controls some 8 green IOTAs on the blue chain. It doesn't mean that it's one address. No, it's 3 different accounts. One is on the layer 2, and one on the pink and one on the blue ledger, the chain. And address with this private key can move IOTAs from those accounts. Of course, anyone can send them IOTAs. It doesn't require any private key, but this address, the wallet, is able to move tokens from now from 3 accounts, right? And the same applies to the smart contracts. This smart contracts has on its native chain account, which it controls, right? And this smart contract also controls the account on blue chain, not native, but controls in the sense that it can withdraw those green 5 tokens back to its native account. Withdraw means, and nobody else can do that. So this is a concept of accounts, which is immediate consequence of multi-chain structure and immediate consequence of the 2-layer system, because we have agents, addresses, and smart contracts who are transacting between layers and between chains, horizontally and vertically. And we have to provide all the security needed for that movement. The only restriction here is actually the smart contract cannot own the tokens on the tangle, on the layer 1. Why? Because there is no way for smart contract to keep a secret key, private key. Smart contracts are identified through the chain consensus, not through private key, individual private key. And the chain consensus owns, it's another story, owns a private key which controls the whole chain. So this is a basic structure which is pretty much gives the feeling how powerful this system could be. And the same way, it's even when you look at it from the bird's fly, it can be pretty complex too. So it's just going back to, so actually what we do, the ISCP account space, or let's say generalized accounts. So account space is a space, includes the order in tangle addresses and each contract is identified by what is called contract ID. It's a pretty natural thing. And each of those contract IDs can own and control some account on each of chains. That's just repeating what I was talking about before. So how we do this now? Actually, we do this with what is called core contracts or default contracts, or whatever is the name for that. They are built-in smart contracts which exist on each chain, and they are deployed together with the chain, but otherwise they are just an ordinary contract. Currently, these are all implemented, and they are implemented as a hard-coded built-in code, and actually it makes sense a lot for that. The 2 contracts are the most important of all 4 of them. Most likely we will have 5th contract with relation to the assembly needs, which is called governance. It's someone has to keep all the relations, contractual relations with validators, with the assembly chains, with the staking contracts, and all that's complicated stuff, which we didn't come to to close yet, but this is a basic stuff which is currently implemented. It's a root contract, is a bootstrap contract or whatever. It initializes the chain. It deploys new upon request. When you deploy new contract, you actually send a request to the root contract and say, please deploy this contract with WebAssembly binary. Please deploy it as a smart contract on the chain. So that's a root contract does. It also handles the chain ownership management, account control, access control list, and so on, and many other stuff which are these administrative, I would say, the core administrative stuff. These are encoded in the root contract. Why we can trust it? Again, I'm just coming back because they all run under the consensus. It's meaning that if we have 50 committee nodes and one root contract suddenly decides to do something different from others, so he will not be taken into account. Oh, this is a consensus. Now on fee management, one of the important stuff. I will come back a little bit about the fee management, how it's implemented, but it's about in the root contract. So another contract is accounts, called accounts. So it maintains all the on-chain ledger accounts and all this machinery behind scenes about the token, ensuring that the consistency of these accounts and the consistency between the layer 1 UTXOs controlled by the chain in the address and the total assets controlled by the chain in the account and so on. So this is what does, it is just like a root account. It has exposed several, actually a lot of public entry points, which is like you can, if you are a wallet on the layer 2, you just can deposit your tokens on any chain. So you're sending deposit request to the accounts contract. And at any time you can send a withdraw request from that accounts contract back to your address, to the layer 1, and nobody else can do that, except because you are identified by your private key. So there are two more technical contracts, but we have many things we are taking as an example the Ethereum functions, like one of it is events. So there is a special part of the WASP node which is called publisher, like ZMQ stuff, ZMQ publisher in the nodes of or MQTT publisher in the Hornet or whatever, which is sends notifications, messages about what's going on in the node. So normally through this publisher, you can you can know that smart contract changed its state, or new smart contract was deployed, or some request was processed. But also it is, all of these events are logged in contract on chain, which means that it's immutable logging. So if you have the whole immutable history of everything what happened through the life of the chain. And this is pretty much just like it works on the Ethereum, more or less. And there is one blob contract. We have to deal with big binaries, because when we do the WebAssembly deployment of WebAssembly contract, they are pretty small now, 30 kilobytes. So they can fit into the request, but it's not practical. So into the transaction. So we provide special contracts which can keep immutable registry of any size of binary objects. For example, WASP binaries. It's not finished, this part. The contract itself is pretty much functional, but the blob part is not finished, and we will have to hook into the interplanetary file system or whatever equivalent is. because you have to handle big binaries without actually touching the tangle, which is you cannot put 1 megabyte into it. Or if you can, then it's not very practical. So that's our core contracts. So that's the machinery behind. Now, just short glance into the structure of the smart contract itself. What the concept, the model of the smart contract. Actually, it's not very much different from whatever smart contracts are in the world. For the purpose, I don't think we can invent something very new, but it's worth mentioning something. So the smart contracts actually is a program. Yeah, and actually it's a smart contract is not a program, but instance of the program with the state. The state has data, arbitrary data. For example, the event log contract can contain the logs of all events for last 2 years or whatever. So it's a state, key data. We call it now data state, and account. So it's owned by the smart contract. Color balance, color balance, color balance. Yeah. Now we have entry points. Normal entry points. This is when you call, and this entry point, you update the state. So it's read-write access to the state from this program, or you can have a view entry points, which you only request a query the state of the contract to return value. It's also, even the term is taken from Ethereum. So it's read-only access to the, so it's normally it is you send I have to check the time. You have several ways to invoke the functions which are programmed in the smart contract. So one of them, okay, there are basically request and call. So call, you are calling from another contract, or you can call from the normally from another contract. You send a request, a transaction, so you do it from wallet or from another smart contract. Or if you want to display, for example, the smart contract, Oracle contract contains the stock market price data for last year. So you just run a web server which displays that Oracle content of this, the chart. So the web server is calling views. So it's another way of calling the entry point. You cannot call the normal entry point at the view. This is so what it's more or less fundamentally the same, like anything else, except maybe, which it's architectural thing. We have some kind of wall between the state, between the host, and between the program, which is called sandbox interface. It's an abstract interface, which is always, the handle of that interface is given to any call, any smart contract. And that smart contract is calling without actually knowing. So it's completely, smart contract is completely abstracted from the, is it what kind of key value store or what kind of the ledger implementation is here. It's completely abstracted through this sandbox interface. So this is also part of the abstraction of the and the part of the model of the IOTA smart contracts. So okay, these are to have understanding what's the difference. Normally you send, not normally, but there is one way of doing this. You sending requests to the smart contracts if you want to call the entry point. And that actually is that the value transaction on the layer 2 is created, and it's of course signed, and that's why we are able to transact between the chains. So the smart contracts are posting requests to each other as an on-tangle messaging, which is trustless and which is securely identified. And as a result, the request finds the way through the tangle to the target smart contract and the entry point, and it's called. Yes, and then there is some effect of changing, updating the state, or sending tokens or whatever else. So this is a request. This is a one way of calling the smart contract. Another is the view. So the difference basically, and even in the low level, is that there is no transaction in between. So you are just giving parameters to the entry point and you call it, but you cannot update this state. You can only retrieve the values from that state or balances or whatever, but you cannot send tokens this way. You cannot do anything else. So this is two ways of doing that. So now this is I just included some short program on the in Rust. Others you can do it in several ways, and you will most likely will have possibility to do in many ways, different ways, because it's at large. So this is agnostic. The core of the smart contracts are agnostic about the way how you program your smart contracts, provided you comply to the requirements of the sandbox. And here is this is a smart contract which has two entry points: store string and get string. One is a stored string, so it's naturally it's an entry point which modifies the state, and this quite complicated Rust code means that you store the string into the key value pair with the key stored string, right? If you want to retrieve that string which you just stored from the smart contract, you call the view entry point get string, and it does the opposite, just looks for that value in the state and retrieves it and returns this value. So the rest here is machinery which actually allows you to for in the Rust to declare your entry points. There are two of them. Entry points, one of them call, another is view. And then the whole program is compiled to the WebAssembly. This specific program is together with all the libraries. It's 28 kilobyte of WebAssembly code, and you just load it into the node in the WASP environment with deploy contract, and you load it on the chain, that 28 kilobytes, and it's running. Now it's maybe I don't know. I would skip this, but just shortly about the token transfers. So we have token transfers, different ways of moving tokens and transacting, different mechanisms. This is, again, you don't have one of them, you have several. So you can move tokens between accounts on the same chain by just calling the entry point, and you just call it and you attach tokens. It's moved on the same chain to another smart contract, all those tokens, and means that you attach them by saying that I send 10 IOTAs and 5 green coins. That's it. This smart contract can send to any address on the value tangle. So there's a special sandbox calls, which means that it adds a output to the transaction, which outputs that to the value tangle, some tokens. You can send tokens from address to value tangle from address of the value tangle to smart contract, and that looks like you are in the wallet, just more or less ordinary wallet like a Shimmer wallet or something, and you just send a request, for example, the deposit request to the chain, and these tokens are going there. And again, between chains, you are posting requests, like I was talking before. So between chains, between smart contracts, the requests are taking the tokens with them and moving them in the trustless way between chains and between contracts. So these are token transfers. Just to finish, told just few more details which might be interesting. They implemented there. Of course, many of these things are experimental, and one of the reasons of this presentation too is to provoke some feedback that maybe we have to do it differently or something. But the fee, it's we know there is a famous thing that IOTA is feeless. Well, this is a extremely good thing, but it's not good thing when you want to prevent from people deploying thousand smart contracts on the chain, or when you don't want it to be spammed, your chain or your smart contract with the thousands of empty requests. So you normally put fees, and you put fees for many reasons. And in the assembly setting, the extension of the ISCP in assembly setting is crucial, because this is a way, a mechanism of how you motivate the validators and stakers to participate in the participating committees. So you collect fees. The fee model is actually pretty simple, that fees are subject, you attach, if required, then you attach fees to the request transaction. Meaning, if you are sending 1,000 IOTAs and some data, and there are requirements for 100 IOTAs fees, so you put those 100 IOTAs on top of those 1,000, and they will become a fees. By default, they are 0. We are feeless. But you can set up, there are two kinds of fees. One is a chain owner fee. Another is a validator fee. So it means that the fees can be collected by validators, then they are distributed among the committee nodes proportionally, or they can be collected by chain owner, or both, or none of them if 0. And the fee currently are set by the chain owner at the level of the smart contract or globally at the level of the chain. And all of these combinations. So it's a function of the root contract, and it authorized, you have concept of the ownership of the chain, and you set the fee, or you make the fee 0. What is here also specific, because it came from the talks about the assembly a bit, that because we need a color for the fee. Normally it's IOTA. Yeah, but I imagine use cases that, for example, I set up a chain and say, look, my chain is very unique, and I only charge fees with this specific token. And I do an ICO of these tokens on the market, and they have value because everyone wants to access my chain. So that's why we have possibility to set a color, chain-wide color, and at the moment of the creation of the chain. By default, if you do nothing, it's just IOTA color. Yeah, and finishing here, I want to say very important stuff. If we are going back to this picture here, right? With this model, let's say we are sending, let's imagine we're sending tokens from address to smart contract, yes? And these tokens are in between. So the concept is that they are has left the address, source address, but didn't reach or wasn't settled in the target smart contract in between. Why is this? Because we have a level, smart contracts are on the level 2. There is no other way to do that. So these tokens suddenly do not belong to no one like that. Yes, so they left my address, but they are not in my smart contract or whatever smart contract. The valid question is, how could I trust it? So, I mean, can it, for example, I sent some tokens and this contract panics. It can panic, by the way, it can crash or whatever, and so on. So what will happen with tokens? So the answer is, because the implementation of the backlog processing is a so-called quasi-atomic, it means that even if we have state in between the transaction, still there is a guarantee that tokens will reach the final destination, the smart contract. But then again, what will happen if it will panic due to bad data or whatever? So are these tokens lost? So this is exception and important topic of the fallback processing, the exception handling on the smart contracts, and we were discussing this stuff. Currently, it's implemented like this: if the smart contract panics, the attached tokens will be returned to the sender automatically with the settlement transaction minus fees. So it will take fees, but will send you the rest back. So this is important for the usability of the whole system, and it is possible only with the IOTA because it's feeless. I mean, you cannot imagine, okay, smart contracts in Ethereum due to level 1 settlement are atomic. So if you are sending something, a transaction won't be settled, the tokens are with you. Here is not, but they will be returned with the next transaction back to you without, only fees are only for transaction, not for the mining. Like I read so in Twitter that someone spent $80 for Ethereum transaction, for small transaction. So this is awful. So here you don't send it. They are returned, less fees, and if fees are 0, they will completely be returned back to you in case the smart contract crashes. So I stop here. I think maybe if you have questions, I'm happy to answer that. Yep, that's it.
Great. No, that was a really good presentation, Evaldas.
Thank you.
Maybe anybody has any technical questions about this?
Not necessarily technical.
or
I have
high
a
level?
question with the interchain links. So essentially, when we have the smart contracts and we are using it to send data to other chains, like I don't know, like what is then the typical like maintenance? Because the software essentially it would be like a one-to-n connection, and probably if other chains would do this, it's an M-to-N connection. Like, is there already some experience with how this would work software-wise? Because when there could be like so many chains which update the software, probably also like smart contract language and so on. And has there been some experience regarding this, how sustainable this is, or if it's in the end more of an ecosystem which is more tending to break, or?
I want, if I understand correctly, you know, here we're talking about cross-chain sending. It's not because this one is Ethereum and this is one is a blockchain, a Bitcoin. These are IOTA chains. So actually, when we're talking about the upgrades and so on, so either we are doing some hard forks or whatever on the value tangle, so we're taking it into account, definitely, or it's up to the policy on the chain, for example, to upgrade smart contracts or to do something. It's a consensus stuff, also governance stuff. So it should be policy, depending on the policy of the chain.
I think, Evaldas, do they, when you request a token from a chain or send to another chain, you basically embed the chain ID in there? And so you send the token out, but it's got the chain ID, so the right chain knows to get that message.
Oh, definitely.
Yeah, I think that's the one-to-many thing. I presume that's what he's talking about.
Yes, I mean, if you are sending the tokens to another, you are invoking smart contract. The smart contract is identified by its target chain, by its chain where it lives, that smart contract. It's an address. Currently, it's an address. In the future, we will have it, will be it color, actually, of the chain. But now it's address of the chain plus the ID of the smart contract on that chain. So this one is absolutely clearly defined the destination immutably on the tangle. This one.
But then like the question is more like, sorry, but if it's like everything is on the tangle, then it's all good. The question was more going in the direction, like for example, if Ethereum would do some changes or another subchain like would do some changes, and who would maintain this, or would it just break at one point? And
no, actually, we have this situation. We are here. Let's say one of our chains is here, and this is Ethereum. So we have this situation, nothing different from what this currently is. So we also are working, discussing with the from Vienna Technical University people about the atomic swaps with outside chains. And I cannot answer your question, what could happen if the Ethereum breaks or changes or whatever it is. Most likely you have to update both sides.
Yeah, and this is by when we have chains like, I don't know, like Polkadot, which are saying to bring together all the other chains. This is always the first thing which popped up in my mind is like, how do you handle all the breaking changes? Because when you want to how to say, build an overarching chain ecosystem in the end, because you're constantly updating all the interfaces, and once it's not done, then essentially everything breaks. So,
but there's like multiple ways to do these cross-chain interoperability, right? And most important is to do assets, and we see that with, for example, wrapped Bitcoin. The way that wrapped Bitcoin works is that it was initiated by BitGo, which is like a custodian. And they, together with some other parties, they basically are those centralized gateways that take your Bitcoin and then just wrap them on ETH, and it's just like a bank, right? Deposits and withdrawal. And with that, Bitcoin from the Bitcoin chain are available on the Ethereum chain and can now be traded on the Ethereum network. And the beauty of ISCP and later on is that we can basically create bridges to any kind of distributed ledger or crypto ecosystem out there, wrap their assets and make it available within the IOTA ecosystem, right?
Yeah. Basically, the difference, this multi-chain environment makes it comfortable for the developers to develop multiple chain environments. But when we bring into the our system some outside chain like Ethereum, or we bring their problems too. But we, of course, we do it. For example, here, if you see my pointer here, we have Ethereum chain, right? And this one, our chain is interface chain with Ethereum. It implements the swap of or liquidity swap or just token swap or whatever.
Okay, now I understood
with
it.
that.
Yeah.
And you have, if Ethereum breaks or something happens, you have to deal with the protocol on this chain. It doesn't, you know, and you do with all chains.
Yeah, thanks. This was the missing part, that essentially we have a link which is still on our side by which we can detect it if the counterpart would break.
I think there's two different issues here, Holger. There's one is if something like Polkadot has multiple chains just like this on the same level one. They've got multiple parachains on their level one ledger. But in Polkadot, you have to pay a fee, I think like 500,000 to reserve a slot. So each of the times that you see these chains putting stuff onto the main ledger, to reserve a slot, you have to pay 500K. We don't need to do that. So everyone
it's
can
also
build
the times that it takes to interact between the parachains is also pretty long. It takes like 1 hour for an interchain call.
And those things are
and it's also not live yet. I mean, it goes live like end 2021, I think. Polkadot doesn't have parachains yet.
Yeah, so
and the thing, even with that,
they don't have, like Polkachain doesn't have any smart contracts yet.
No,
they do have,
Polkadot was just an example. It could also be Cosmos or like any other tech which claims to be.
So the issue there is the fees, and the base layer for most of these is a single ledger. So what we're building here is like multiple levels of scalability. So you can scale this by, like Ethereum's got multiple chains, like roll-up chains where you can do like second layer processing. We've got that. We've also got scalability, the fact that we've got a DAG rather than a blockchain at the base. And when you add in sharding on top of that, it's like you got, I won't say infinite scalability, but many levels more than the others, and no fees.
I think the most interesting aspect is also like you have your identity established on the layer one, and you can run multiple nodes processing different smart contracts in this, like in parallel, and also having just more resource, like just throw more resources at more smart contracts, but still leveraging on the same identity that you have. So in Ethereum, you have one identity in your shard, and you have to execute everything. Here you have your one identity, and you can run 100 machines that all leverage on the same identity and split up your computing power on different smart contracts.
This is awesome.
Yeah.
There's a lot more when you bring in the whole. There's so much more to this. Yeah, I mean, as in like when you bring in like the staking bit and all of that, and how this helps to secure the layer one, it's a complete game changer. And I think I'm very excited to get it more public, but we need to get it a bit more concrete before we do that.
Yeah. Actually, what is missing? There are now we have final touches on the basic library on the Rust programming environment. It's gonna be pretty universal. You can do everything. Maybe it's not perfect in terms of the, I mean, some other specs, some user experience or whatever, but it's gonna be, so we have to put a finishing touches on that, and we have to write at least some documentation. I mean, tutorials and so on, and it's taking time and of course. Otherwise, it's we have some. I skipped the part about the tooling. Now we have a pretty good tooling for the smart contract unit testing. So all the tutorials will be based around that, and you can do all smart contract in multi-chain environment, native environment, all development, all possible. Your protocols on the just simple Go testing tool. I mean, you can deploy 5 chains on the test, you can send requests, you can assert states, you can do whatever. So this is one tool. Next tool level is that we have a possibility to run this many chains on one WASP node. I mean, the committee is one node, and then you can develop it. And when it will be ready, so basically I expect it to tell the community that please look at it and maybe you can create things with it. And of course,
I've got a question. How hard would it be to add different VMs later on? Like, is the whole consensus stuff agnostic to the VM itself, or is that very much hardware?
It's very agnostic. This part, actually, it's not. I'm not prepared for that part with pictures to say. But currently, you can write them or hard coded. Write Go calls to the sandbox interface, or you can write with Rust. Also, Eric implemented with Go and with Java, I think even. So it all comes down to the sandbox interface and ability to put the whole program into the binary, loadable binary, and linkable, dynamically linkable binary. So it should not be even WebAssembly. It can be something else, theoretically. But practically, of course, it brings about a lot of complexities at this level, which is sometimes may be not practical. We don't know.
Just a bit of news. It's today. Hopefully, we're signing an ecosystem development fund for another team to come in and build another VM as well. And so I think that should hopefully prove or tell us how difficult it will be. And they'll also be helping with the main development, but I think that should help prove this concept.
Yeah, there's a lot of development still, not only on the, extension part like VM, but also on the core, because there are many aspects, even in the very core, in the state, for example, at the Merkle proofs of the state, or snapshotting, or the so-called blob data type, all kind of stuff we have to develop too. So, this is still at the early stage, I consider. So, okay, I think it's over. Jakub, what would you? So, thanks, everyone.
Yeah, thanks a lot for the presentation, Evaldas. And maybe you can compile this to a PDF and then maybe share it in IF General, the presentation, so that others can also look at it.
That's what yes, sure, definitely. Yeah. I can do that.
That'd be really great. Yeah.
Okay, I will do immediately. Okay, then
awesome. Thanks a lot.
I wish everyone nice weekend. I don't know if you have it, but we have a lot of snow here at last.
That's good.
That's good. Yes, definitely.
Let's make some snowman.
Let's make some snowman.
All right. Have a good day, everyone.
Perfect.
Bye-bye.
Thanks, everyone. Bye-bye.
Okay.
Thanks, Evaldas.
Bye.
Thanks,
Bye.
Evaldas.